Hello, let's continue our discussion on continuity. And really quickly, thing to talk about, when talking about continuity, the first step is to show that the value itself exists. The second step is to show that the limit as we approach some x value of our function also exists. And so if we have a function like right here, here's x equals c right there, we want to make sure that one, we have a value and that we are approaching that value. That's our limit. And the last one is to show that the value equals the limit as x approaches c of our function. Now, so we talked a bit about these yesterday, so we'll just take a look at a couple more examples right over here. The definition, use a definition of continuity to determine if the following are continuous. Now I'm going to go through these pretty quickly. We saw this yesterday. So if you just slow it down or pause it, go ahead. The first step, just check for the value. Well, that's where it equals 1, right here at 1. So that's going to become 3 minus 1, which is 2. So we do have a value here. The second step is to check the limit. 1, because this is piecewise, we're going to approach from both sides, the right and the left side. So if we have 1, remember this, 1 is on, we have the right, we have the left side and we have the right side, less than, greater than. That's from yesterday's notes. So if we're less than, that's going to put us on the bottom one. So to the left. So that's going to put us on x squared plus 2x. See if that's going to equal the limit as x approaches 1 from the right. And that's going to be, of course, the top function, 3 minus x. Plugging in the 1, we're going to get, what's that? Just 1 plus 2 equal to 3 minus 1, so we can get 3 equals 2, which obviously is not true. So therefore, the limit here does not exist, right? We know that the limit, therefore, does not exist because the left and the right are approaching different values. So our answer will be, therefore, the function f of x is not continuous at x equals 1, and that is because the limit as x approaches 1 of our function does not exist. And there's our answer right there. Pretty simple to do. Taking a look at number 2, we want to find out if the limit here exists at 0 and at 2. But first, we're going to talk about, well, what shape is this? Hopefully you might remember that this is a semicircle, right? With a radius of 2. And it's the top half because it's positive. We'll discuss more about that later on. So there's our semicircle. There's 0 and there's 2. So for c equals 0, yeah. Now I'm not going to do this one here because I know that that's going to be continuous, and you can do your rule. I want to talk about, what about c equals 2? That's a big one. First of all, look for the value. F of 2, that's going to become the square root of 4 minus 2 squared, which is 4, which is 0. Square root of 0 is just 0. But the second part is what's really tough. The limit as x approaches 2 of our function. And in this case right here, the limit, now this is a tough one, is going to be d and e. And that is because the limit does not exist here, mainly because there is no right side. The limit as x approaches from 2 from the right of our function does not exist. Therefore, this cannot have a limit because there's no right side. Remember, the definition for a limit says that the right and the left have to approach the same value. Well, here I have a left side, but there is no right side. So the limit can't exist. So we can say, therefore, f of x is not considered continuous at x equals 2, and that is because the limit as x approaches 2 of our function does not exist. That's kind of a tough one right there. So if you need to watch that one again, please feel free and go ahead and do that. All right, so our next take a look at examples. Now we've been talking about continuity. Well, now let's talk about what's called a discontinuity. And there are 3 main ones. We have point, jump, and asymptotic. There's also another one, none of the above. We'll talk about that just a little bit later on today. So if a function is not continuous at x equals c, then there must exist a discontinuity at x equals c. In other words, there is a reason why f of x is not continuous. And that's what we're looking to find here. In other words, one or more parts of the definition fails. And we're going to talk about that. This is on a quiz and on a test about the failure of continuity. There are three main types. The first one is point, sometimes referred to as a whole. So we want to be more fancy, so we can say point discontinuity. And of course, if I could draw that, it would look something like this. At x equals c, there is a whole. An example of an equation, something like x squared minus 4 over x minus 2. In other words, what can happen here is we can cancel a common factor. Right there. In other words, because I can cancel a common factor, we actually have a special name for this. It is a removable discontinuity. Matter of fact, a whole is sometimes referred to as a removable discontinuity. I can cancel something out. So the question is, well, which part of continuity here fails? We'll talk about that. I guess we'll talk about that in a second here. The next type is the Mac Daddy of them all, jump. So at C, I could have a jump. Mac Daddy make you jump, jump. Look up the song Crisscross Jump, greatest song from the 90s. You'll enjoy it, I promise. Okay, so there it is, the Mac Daddy of them all makes you jump. Well, an example of this one is that weird absolute value function that you guys learned last year, right? Remember this one? It would look like this. At 0, we would have something like this. Or sometimes the greatest integer function. Now, in either case, I wasn't able to factor and cancel like I did on the whole. So we call this one a non-removable discontinuity. Non-removable. And the last one we're going to talk about is asymptotic. Now, asymptotic is pretty easy. If we have a function there approaching like a little bit of an asymptote right here, of course, this is like 1 over x. And same thing, asymptotic is also non-removable. What we mean by removable is that I can remove a factor. Like over here, I can factor x plus 2, right? X plus 2, x minus 2 over x minus 2. And I can remove that factor. So that's what we call it, this removable, but these are non-removable because nothing could cancel. So in other words, only point discontinuity is what we call removable. Right there. Now, I want to talk about the following. Which part of the definition fails? For example, like in a point discontinuity, what part of the definition fails? In this case right here, the value does not exist. So we could say f of c does not exist. For the jump discontinuity, in terms of the definition, we would say that the limit itself does not exist. In asymptotic, a couple ways. One, you could actually say the value at c does not exist, or you can say that the limit itself does not exist. Either case here, because over here, remember, asymptotes cannot have a limit on them because you're never approaching a certain value. So we say that the limit at asymptotes do not exist. So notice when I say what part fails, I specifically either the value, the limit, or the value limit. And there's the other one, that the limit does not equal the value. For example, if I had a point up here somewhere, it has a value and a limit, they're just not equal. You're going to see a question like that, I promise. Okay, so I'm going to go ahead and take a pause for right now, and you can go on to section 2 and take a look at those notes.